This lesson deals with supplemental problem 8.15. You can find this problem in the ECE202 ebook in the Chapter 8 Supplemental Problem starting on page 22. Consider this equivalent circuit for an electric fence for repelling sharks. What I've got here is the electronic fence, which has an input of a 340 volt cosine at 60 Hertz, or 377 radians per second, 2 C's and an L, and then I've got a long set of wires that are in the water and have a fairly low resistance, and if the shark brushes across these things, then a current will flow through the skin of the shark. I'm going to estimate the skin of the shark with the salt water around about 100 ohms. This is supposedly an environmentally acceptable way to repel sharks along coastal waters, but let's see what kind of value of current we're looking at through the skin of the shark. Okay, so first find I of shark of t in steady state by using source transformations to reduce the above circuit to the following. We've got a current source and an impedance, and then we've got our load. We'll find the current in here using the current divider. Let's repeat the same problem and find I of shark of t in steady state by using a Thevenin equivalent circuit of the fence. That is, find the open circuit voltage and the impedance, and then solve for the loop current, which is the current in the shark. Then lastly, let's form the mesh equations by inspection, and let's use MATLAB to find the phasor value of I of shark. So let's solve for I of shark using our 3-step algorithm. So the first step is to transform from the time domain to the frequency domain. We got a 340 volt cosine at angle 0, frequency of 377 radians per second. We have a capacitor whose value is 100 microfarads, minus J over omega C. Turns out to be minus J 26.53 ohms. Have an inductor, J omega L, where L is 250 millihenries. I wind up getting a J 94.25 ohms. And then lastly, this 2 microfarad capacitor, minus J over omega C, is a minus J 1.326K. The wires connecting our electric fence to the shark have a fairly low resistance, so we'll treat them as short circuits, and then our load here is about 100 ohms. We want to find the current in the skin of the shark. Our second step is to do the analysis, and it's suggested that we do source transformations to do this, so let's try it. We'll take this voltage source in series with this impedance and convert it into a current source in parallel with the same impedance. I got the minus J 26.53, and then I've got 340 at angle 0 divided by magnitude of 26.53, and the angle is minus 90 degrees. So this ratio is 12.82. Angle of the numerator minus the angle of the denominator, get 90 degrees. I've got these two in parallel. I did the source transformation. I'm going to replace this by a single impedance. So I'll take the product over the sum. I get a J squared and another minus sign here, so I get 2.5K. And then the sum of these two is a positive 67.72. 1 over J is minus J, and this ratio is 36.92. I can source transform again, convert this current source in parallel with this single impedance into a voltage source with that same impedance. So here I've got a negative imaginary impedance, so it's going to be a capacitor. My voltage source is going to be the product of this current, which is 12.82 at angle 90, times this impedance, which is 36.92, and the angle is minus 90 degrees in polar form. Product of these two is 473.3, and then the angle actually is equal to 0. I can combine these two into one capacitor, whose value is minus J 1.363K. Let's do one more source transformation of this current divider. Take the voltage divided by the impedance, the minus J term here, and get 347 milli at angle 90, and I got the same impedance here, and I got my 100 ohms. Now the current divider, if we use the impedance one, is going to take the other impedance, which is going to be the capacitor in this case, over the sum of the two times the current, and that's going to be the current in this element. Again, that's our impedance current divider. This is equal to 1.363K at angle minus 90. And then I put this into polar form, a little bit longer than this, but not much, so it's 1.367K. And the angle is going to be in the fourth quadrant because this is negative, and this is a lot longer than this, so it'll be closer to minus 90. Take this times this divided by this. This is about 1, so a little bit smaller here, 346 milli, and then 90 and minus 90 is just 0, and then minus the denominator, I get a plus 85.8. So then our time domain result then is to take the magnitude and the angle and put the cosine of omega t between it. Now it takes about 40 milliamps to stop a human heart. This is going to say current going from one arm through your chest and then out the other arm. For the shark here, we've got this really going on the outer skin. But this is about a factor of 10 larger than it would take to stop a human heart. But again, it's not going through the heart of the shark, just on the skin of it. My guess is it's going to really hurt. This is the solution for using source transformations. Our next approach is to find a Thevenin equivalent circuit. So we'll take the circuit in step 1 and remove the load and find the open circuit voltage and then find the impedance looking back with all the independent sources set equal to 0. Since there's no current going in my open circuit, then the voltage here is the same as the voltage here. I'll call that V sub L, which is the voltage of the inductor. So I've got a voltage divider. I've got 340 at angle 0, and I've got this impedance, which is J 94.25, and then adding that to the capacitor impedance of minus J 26.53. So combining these two, I get a J 67.72, And then divide the J out, and then my ratio here is 1.392, and I'll multiply that by my 340 at angle 0. I get 473.2 at angle 0. Setting the independent source equal to 0, that's shorting the voltage source. And that's going to make these two impedances in parallel, and that's in series with this. So I'm going to add this to the product over the sum. We already found this combination in the previous calculation. That was a minus J 36.92. So adding these two together, I get a minus J 1.363K. Now I have my Thevenin equivalent circuit with my Thevenin voltage and my Thevenin impedance, and now I put the load back on, and I could find the loop current in here by taking the voltage and dividing by the total impedance. So adding these two together, which we've done before, we have a magnitude of 1.367K, and the angle is minus 85.8. So the ratio of these two turns out to be 346 milliamps, and again the angle is just the angle of the numerator minus the angle of the denominator, which is a plus 85.8. And so then our step 3, putting the cosine of omega t between the magnitude and the angle, we find the same result we found previously. And then lastly, let's find the phasor value of the shark current using mesh equations by inspection. So we'll take our circuit from step 1 in part A and assign mesh current, say I1 here, and mesh current I2 here. And then our mesh current I2 is the same as our unknown here, I of shark. Set up a blank 2x2 matrix. And what's going to go in row 1, column 1 is the sum of the impedances in mesh number 1. And that's going to be the capacitor plus the inductor impedance. Now what's between meshes 1 and 2 will go in row 1, column 2, but negated. So it's going to be a minus J 94.25. Then if you go around the mesh counterclockwise, record the first sign you see, and that's going to be a plus 340 at angle 0. But for MATLAB, we're going to need this in rectangular form, and that'd be 340 plus J0. Go around mesh 2 and add up all the impedances. That's going to be the 100 ohms, and then I've got these two impedances of the capacitor and the inductor. And if you go around the mesh counterclockwise, there are no voltage sources, and it's just 0, which is 0 plus J0. Combine all the things here. So adding these two, we get a J 67.2, and adding these two, we get a minus J 1.232K. So I got a 2x2 matrix. We can type the entries here, or we could put this into an M file. So here's row 1, column 1. That's my value of the impedance right here. But again, the number comes first, and then the J comes second. So 67.72 J. This entry is minus 94.25 J, and that's in row 1, column 2. And then in row 2, column 1, I've got minus 94.25. Again, the same thing I had over here because it's symmetric. And that's going to be row 2, column 1. And then lastly, I take this entry here, which is 100 minus 1,232 times J. I use a semicolon here, so when I hit return, I won't echo it back. And then my voltage is just going to be a vector with 340 plus J0, and then 0 plus J0, just 0. And then to find the current, I'm going to do matrix division. So remember, you're going to take the matrix here, which I'll call Z, and this is my voltage vector V. I'm going to take Z backslash V, and that'll give me a current vector, which will be in rectangular form, and the results are shown here. You can also convert that to polar form by taking the ABS function of the current vector, and then likewise for the angle, taking the angle and then multiplying it by 180 divided by pi. And the results are shown here on the right-hand side. And you can see here for my current I2, I have a magnitude of 346.2 milliamps at an angle of 85.8044 degrees. That's the same as parts A and B. And this is supplemental problem 815.